This fact was prepared for the linear and switching circuits unit of the electronics combined framework at Bournemouth University. It's one of 3 related facts covering the analysis of a simple JFET amplifier circuit. The objective for this part is to perform a DC analysis to find the quiescent operating point of the circuit. With this information, we can go on in part 2 to derive the transistor model, which you can apply in part 3 to find out the amplifier gains, input and output impedances, and output voltage. This is the circuit example we'll analyze. The JFET parameters are the saturation drain current, IDSS, which is 12 milliamps in this case, and the pinch-off voltage, VP, which is -4 volts. The first thing to do for a DC analysis is to open circuit the capacitors. The next thing to notice is that the gate resistor, RG, will effectively connect the gate to the 0-volt line. This is because the nanoamps of leakage current which flow through it can only set up a voltage drop of a few millivolts, which we can safely ignore here. So after removing the isolated components, we're left with this simplified circuit. Remember that effectively no current flows through the gate, so that the drain current, ID, flows down from the supply, through the drain resistor, RD, through the transistor, and then the source resistor, RS, to ground. The volt drop of the source with respect to the gate, that's VSG, is equal to the volt drop across the source resistor, VS, since they're both equal to the voltage of the source terminal with respect to 0 volts. Now the volt drop across RS, owing to the drain current flowing through it, is ID times RS. However, we don't need to know the voltage of the source with respect to the gate, VSG, but we want it the other way around, that is, the voltage of the gate with respect to the source, VGS. The final result here is that VGS, the circuit voltage which controls the current flowing through the JFET, is equal to -ID times the source resistor, RS. Now the output drain current for the JFET produced by applying the gate voltage VGS is given by the nonlinear square law characteristic shown in this slide. This is bounded at one end by the saturation drain current IDSS and at the other by the pinch-off voltage VP. The equation of this characteristic can be written as shown here. You might like to check the equation works by entering VGS is VP and solving to confirm that the drain current ID is 0, or by entering ID equals 0 when you should get VGS is VP. Now this characteristic will tell us the value of the drain current for any given value of gate voltage. However, the gate voltage VGS is determined by the circuit through the result we obtained in the previous slide, that is, that VGS is -ID times RS. We can plot this on the same graph by writing it in terms of the drain current as ID is minus VGS over RS, a straight line with drain current increasing as the gate voltage becomes more negative. The operating point of the circuit we are looking for will then be where both of these relationships are satisfied, and this is at the crossing point of the JFET characteristic with the circuit plot. Or we can solve analytically if we substitute -ID times RS for VGS into the JFET square law equation to obtain a quadratic equation in terms of the drain current ID. We can then solve this quadratic to find the DC operating point values of IDQ and VGSQ. On first, or even perhaps at second sight, this quadratic looks a bit nasty. However, it's actually just a straightforward quadratic equation of the type a times x squared plus b times x plus c equals 0, where the unknown x is the drain current ID we need to solve for. If we compare the terms, we should be able to see that A is equivalent to Rs squared, B is the bracketed term of twice Rs times Vp minus Vp squared over IDSS, and finally, C is equal to Vp squared. The solution for the drain current is then found using the standard quadratic formula. So all we need to do is to calculate the coefficients A, B, and C from the parameters Vp, IDSS, and Rs, and then solve the standard quadratic to find our solution for the quiescent DC drain current, IDQ. In our example, Rs is 1.5K, so squaring it gives 4.84 million. B works out to be minus 18,933, while C is 16. Putting these values back into the standard formula gives two possible results of 1.2 milliamps or 2.7 milliamps, depending on whether we take the positive or negative root solution. If you want to use MATLAB to find these results in Servo Calculator, this is the code you'll need. Now the only thing left to do is to choose between the two possible solutions. To do this, we simply need to put the values found for ID back into the circuit to see which one works. The first possible solution of IDQ is 1.2 milliamps gives a quiescent gate voltage of minus 2.72 volts. This is within the permissible range of 0 out to the pinch-off at minus 4 volts. The drain voltage works out as 16 volts, which is a bit high, but okay provided the output signal voltage is less than a volt or two. The second possible solution of IDQ is 2.7 milliamps gives a quiescent gate voltage of minus 5.89 volts, which is not within the permissible operating range of 0 to minus 4 volts, and it's therefore the wrong one, even though the drain voltage looks quite reasonable. Hence, the DC operating point of this circuit is with a DC drain current of 1.2 milliamps, a gate voltage of minus 2.7 volts, and a drain voltage of 16 volts. Finally, here's an example for you to try. Hopefully your solution should match that at the bottom of the screen, but please don't look yet. Good luck. Thank you.